Yeah, thanks so much, Sebastian. So I'm excited to be here today. Thanks for the invitation, Sebastian, and also Bart, and for organizing a great series of talks. So today I'll be talking about our work, which is focused on wind farm wake steering control under transient atmospheric conditions, so atmospheric conditions which are evolving in time. And as mentioned, I'm an assistant professor at MIT in the Department of Civil and Environmental Engineering. So as we know, wind turbines are often placed in close proximity in wind farm configurations due to the costs associated with transmission lines and land costs and other practical constraints that constrain wind farm development. However, all utility scale wind turbines in the world are controlled as if they're completely isolated. And the well-known result of that is visualized in this top view of a wake model where the flow is from left to right, and this is at hub height, where we can see that each individual turbine in this wind farm is generating an energy deficit wake region. And when that energy deficit wake region is transported into the downwind generators, those turbines are seeing lower incident wind speed and therefore produce lower power. So this represents an efficiency loss for the collective farm. So we've been interested in methodologies to alleviate these wake interactions through wind farm control. And in particular, we've been focusing on wake steering, where we intentionally yaw misalign certain turbines in the wind farm with respect to yaw angle gamma between the turbine orientation and the incident wind direction. That laterally deflects or steers that energy deficit region away from potential downwind generators. Where the goal of such an approach will be, for example, the focus of our studies is to maximize the collective power production of the wind farm, subject to the yaw misalignment decision of each individual turbine within that wind farm. And our approach primarily is focused on leveraging wake models or computationally efficient low fidelity models, which represent the flow physics in this wind farm to select our control strategy. And the core challenge with selecting a wind farm control strategy based on wake models is that wake models fundamentally parameterize physical processes in the atmosphere. So a good example of this is that they parameterize turbulence in the atmosphere and also in the wind farm flows through a wake spreading coefficient. And so our research question is, how do we select the optimal operation for the wind farm, the optimal yaw misalignment angles, in the time-varying atmospheric boundary layer, the atmospheric boundary layer which is evolving its mean state in time. And so I just want to highlight a few of the leading order wind conditions which can influence the wake dynamics in the wind farm and therefore influence the optimal control strategy. So if we start with a standard base case, here again, a wake model with flow from left to right, for standard operation in region 2, where the turbines are in a line and are interacting with each other, we can visualize the effect of a few different atmospheric conditions on this wake interaction. So we can start by looking at the effect of wind speed. As we start to increase the wind speed, we see that the turbine thrust, the coefficient of thrust here visualized, starts to go down, and it goes down non-linearly. And so we can see that as we increase the wind speed, for example, the thrust that each individual turbine imparts on the wind will go down, and therefore the magnitude of wake losses will go down. And so we expect that for different wind speeds, we expect our control strategy to change. Here I've visualized what the flow is from left to right in this image, but if it was coming from the top of the page, I've rotated what the wind farm looks like in that setting. And of course, we can now see that there's actually no wake interactions between these turbines. And so we might expect a different control strategy, whether the wind was from the left to right or from the top, as visualized on this right-hand side. And of course, another primary influence in the atmosphere is the turbulence intensity. So from the left to the right, I've increased the turbulence intensity or the degree of wake recovery and wake spreading in this wake model visualization. And we can see that the wake interactions are less severe and therefore this will affect the control strategy. So how has this been handled in the past in the context of wake steering control? So the standard approach to incorporate these atmospheric conditions that I mentioned on the previous slide has been to use an open loop control strategy where we have some controller which has some low fidelity wake model baked in. We input, it's a parametric wake model, it inputs wind speed and wind direction, which has the influences that I showed in the previous slide. But we also need to know what the wake model parameters are, and in particular, the wake spreading rate, which dictates the wake recovery. And how this has been handled in the past is that the wake recovery has been estimated using an empirical function, which depends on the turbulence intensity. So the turbulence intensity is fed in, an empirical function estimates the wake model parameters, that then is fed into the control, which along with the wind speed and wind direction, is then able to estimate the best yaw misalignment strategy for the wind farm. And so what does this estimation of this empirical function look like in practice in traditional wake model tuning? In practice, in the past, this has looked like estimating wake model parameters in idealized controlled experiments. And those parameters could be this wake spreading rate, which I've mentioned a few times now, but it could also be other parameters which exist in these wake models. So for example, this power-yaw cosine exponent, if you're interested in the power production of a yaw misaligned turbine, or again, it could be this wake spreading rate. And so this very nice paper gave us an instructive introduction into this domain where they compared a wake model to large-eddy simulations in offline tuning experiment. And they actually showed very nicely that the wake growth rate, this wake spreading rate in their wake model compared to their simulations varies pretty much linearly with the turbulence intensity. And so this function up here would then be the empirical function that would be used on the previous slide. And this paper has proposed this function. It's been used many times in the past. But it's worth noting that the authors highlighted that this calibration was performed using large-eddy simulations with a neutral atmospheric ground layer. So this inherently neglects certain properties which exist in the true atmospheric ground layer. And the effects that are often neglected in traditional wake model tuning more broadly are stratification, wind speed shear, wind direction shear, partial wake interactions, and other atmospheric ground layer effects which may exist in real operational wind farms. And so in this particular talk, I'll focus on stratification and also wind shear in parts 1 and 2, and I won't discuss the others. And so coming to the outline, in the first part of this talk, I'll discuss our work developing a closed loop wake steering control strategy with a focus on characterizing the role of the atmospheric stability on the wake recovery. Then I'll discuss our work in power-yaw modeling, which is aiming to elucidate the effects of atmospheric ground layer wind shear on the power production of yaw misaligned turbines and wind turbines more broadly. And then I'll wrap up with some conclusions and next steps. And so again, returning to our primary question, we're interested in selecting the optimal operation of the wind farm, and in particular, the optimal yaw misalignment angles in the time-varying atmospheric ground layer. And so for that, we proposed a closed loop control strategy, where we have the wind farm, which is operating at time. It sends its power production measurements in the form of SCADA data, if it's a utility scale wind farm, and also wind conditions. That's then fed into a parameter estimation routine, which estimates the model parameters that are relevant for the turbine wake model, the control strategy. The controller then estimates the yaw misalignment angles in time, which are then fed also to the parameter estimation and to the actual wind farm to impose. And so the key 3 strategies that we use in this closed loop control methodology we've proposed are that we do parameter calibration uncertainty quantification based on the measured wind farm data. And we do this in a closed loop fashion in time. We also use a gradient-based optimization methodology, which is proposed in this 2019 paper to enable real-time wind farm control. And we also do wind condition forecasting so that we make control decisions based on what's going to happen, or at least our best estimate of what's going to happen in the future, rather than some kind of moving average of what's happened in the past. So I won't talk much about the wind condition forecasting in this talk, but details of that can be seen in this recent wind energy science paper. And so instead of the tuning in an offline setting, which has been done in the past, we approach the parameter estimation more as an optimization problem, or alternatively, you can call it an inverse problem, where we consider that we have some data Y and some model G, which depends on some unknown parameters theta. And the goal, very simply, of our approach is to minimize the data space objective function. So we want to find this theta star that gives the minimum value, the minimum discrepancy between the data that we're measuring and our parametric wake model. And it's worth noting that this objective function can, of course, be generalized to incorporate regularization, model error, and so on. And this can be solved in a variety of different ways. One can use gradient-based optimization to estimate theta star, derivative-free approaches. And in this particular talk, we're actually going to use the ensemble-Kalman filter as a parameter estimation methodology for this dynamical system. But we can go beyond just estimating a single value of theta star. We can actually estimate a probability distribution of theta star, or of theta, called a posterior distribution of the model parameters, rather than just a single value of theta. We were really interested in what's the probability distribution of that theta, or more particularly, the conditional probability distribution of theta given the measurement of data Y. And so if we make several assumptions, for example, a Gaussian prior distribution and Gaussian noise based on central limit theorem arguments, then we can find that the posterior distribution is proportional to the exponential of the negative objective function that I showed in the previous slide. And so we've applied this in this JRSE paper in 2021, where we have some measured SCADA data in black The blue, which you can't see very well, it's behind all the red dots, but it's essentially at the same points as the red dots, is the predictions of the wake model when we just estimate theta star. So what's the theta values, the parameter values that give us the lowest data space error. And then in red, we're actually using the wake model predictions over a probability distribution of the model parameters given this conditional probability distribution, the posterior distribution. So we can see it doesn't just estimate the mean, but it also has some uncertainty associated with the wake model predictions. And what's nice about estimating the uncertainty of the wake model predictions is then you can actually perform wake steering strategy where you're not just maximizing the power production of the wind farm, but you're maximizing the expected value of the power production of the wind farm conditioned on the posterior distribution of the wake model parameters. And so that's what we did in this JRSE paper in 2021. And we found that incorporating the uncertainty in the wake model parameters increases energy production overall during our wake steering studies. It also improved the robustness of the control and quantifies the prediction uncertainty. So lastly, in terms of the closed loop control strategy that we've been developing, I wanted to just quickly mention how we actually optimize the yaw misalignment angles. And so in this 2019 PNAS paper, we developed an optimization strategy which is based on analytical gradients so that we can perform real-time control. And so the key details of this are that we have an analytical wake model forward pass, which predicts the power production of the wind farm subject to the yaw misalignment decisions of each individual turbine. Then we have a backward pass where we compute analytical gradients of that power production. So partial of the power production with respect to the yaw misalignment decision of each individual turbine on the farm. And that's computed through a successive application of the chain rule. Then we perform a gradient update. For example, we're using atom optimization, but you could use whatever gradient update methodology you prefer. And that gives us a new yaw misalignment angle. And we can repeat this until we demonstrate convergence. And one of the nice things about doing gradient-based optimization is that it generalizes quite easily actually to incorporate the uncertainty that I mentioned on the previous slide. So if instead of just having a single value of theta, we can generalize this to maximize the expected value of the power production over the probability distribution of those model parameters. So that's our general closed loop wind farm control setup. We're quite interested to see how well it performs. And for that, we used large-eddy simulation as a testbed control testing environment. And so we use our in-house large-eddy simulation code called PEDAOPS, which is a high-order pseudospectral large-eddy simulation code, which simulates the stratified atmospheric boundary layer with full Coriolis effects. And we simulate finite wind farm behavior with a concurrent precursor methodology. And so first, we focused on conventionally neutral atmospheric boundary layer, and then we focused on diurnal cycles. So I'll explain a little bit more about each of those right now. So to start with, we focused on the so-called conventionally neutral atmospheric boundary layer, which incorporates stratification and Coriolis effects, but there's no surface heating. And so the mean statistics in this atmospheric boundary layer are quasi-stationary. So they're not evolving significantly in time, except for the effects, of course, of turbulence and of inertial oscillations from Coriolis effects. And so this is a nice testbed environment because the mean states aren't evolving. So we have a fairly well-defined behavior of the controller for testing closed loop control versus open loop control. So I won't talk much about the conventionally neutral test cases that can be seen in this 2020 wind energy science paper. But instead, we're more interested in presenting results related to the time varying atmospheric boundary layer. And so for that, we were simulating a diurnal cycle where we have heat flux variations at the surface, which will actually change the statistics in the atmospheric boundary layer as a function of time. So the mean wind speed, the wind profile, shear, veer, and also other details, and it'll change the stability. And so we initialized this simulation of this wind farm with an unstable atmospheric boundary layer, which we can see here visualized in this instantaneous snapshot at hub height. And we can see that there's substantial turbulence in the unstable boundary layer. So we have convective behavior. There's large length scales associated with this and a very high turbulence intensity. And if we just look at the mean wind speed profile from this domain, we can see that in the rotor area, which is down here in between these red lines, there's very little wind shear, and the profile is very well mixed as a result of the convective atmospheric boundary layer properties and the high turbulence. As the simulation evolves, we turn on surface cooling. So this flow transitions naturally from daytime convective atmospheric boundary layer to a nocturnal boundary layer. And we can see that that significantly changes, of course, the qualitative picture of this atmospheric boundary layer and of these wake interactions. So now the turbulence is suppressed by the stratification instead of being enhanced by convection. And we can also see that the wind direction has changed. For example, instead of flow being from left to right, the flow is actually coming from the corner of the domain. But the other effect is that it changes the mean properties of the atmospheric boundary layer profiles. For example, the wind speed. So going from lighter to darker is going from daytime to nighttime. And we can see that the wind shear over the rotor area has been substantially enhanced by moving to the nocturnal atmospheric boundary layer. I mentioned that the wind direction changes as a result of the stability change. And also the wind direction change over the rotor area. So the wind direction shear changes as well. So during the daytime, when we're very well mixed, we have very little wind direction shear over the rotor area. But as we transition to this nocturnal boundary layer, we have substantial wind direction variations over that rotor area. So the question is, how does the wake model parameter estimation perform in this type of environment where the flow states are naturally evolving? And so this is a bit of a busy plot. So I'm going to walk through what each line is step by step. So here's the wind farm setup that we immersed in this diurnal cycle atmospheric boundary layer simulation. I'm going to focus particularly on the power production of turbine 1 and of turbine 4 here. And so turbine 1 will always be free stream with respect to incoming wind, which is either coming from left to right or from the bottom left corner of the domain, depending on the time in the simulation. And turbine 4 will either be in the wake of turbine 2 or in the wake of turbine 1. And so here I've plotted 3 different things. The solid lines are the LES power production for a case where we impose wake steering. The dots are the wake model predictions aided by the parameter estimation methodology that I introduced a few slides ago. So that's the dots on top of the solid line. So we can see it agrees quite well. Then the dashed line is for reference. It's a large-eddy simulation power production case where we impose yaw-aligned behavior. So the wind turbines are always trying to yaw-align themselves and maximize their own power production. So we can see generally, of course, that the wake model is performing fairly well at estimating the power production in the wake steering case. And we can also see the characteristic signs of wake steering. So the power production of this yaw misaligned turbine, turbine 1, has decreased compared to the yaw-aligned case, but the power production of the downwind turbine has increased. And so what's interesting is to look at actually the wake spreading rate in this case, which is being estimated continuously in time. And we can see that in the initial part of the simulation, this represents the unstable period of the simulation. The wake spreading rate is quite high. And then as it transitions to this nocturnal stable atmospheric boundary layer with suppressed mixing, that wake spreading rate drops quite quickly and then maintains approximately flat during that stable boundary layer period. So then how does this actually affect the wake model predictions, comparing the estimation methodology that we're using with the ensemble Kalman filter versus the traditional offline calibration approach? So that's what's being plotted here, where the bars are the data from large-eddy simulation. In blue, I have yaw aligned, and in red, I have the wake steering case. And then the dots represent the wake model predictions. So we can see that the wake model is generally capturing the trends associated with both the wake steering and the yaw-aligned case. And if we compare that to the predictions associated with an empirical pre-calibration where the wake model parameters are estimated based on the turbulence intensity in the atmospheric boundary layer, which again is evolving in time, we can see that there's a much higher predictive bias associated with this pre-calibration, moving to this case of stability. And in particular, in this particular study, we showed that this is approximately a 4 times reduction in error when we're using the active estimation of these parameters in time. And so the final question, aside from the predictive capabilities of the wake model, is how does this all influence the power production when we're doing wake steering control? And so here we're showing the differences between the open loop and closed loop methodologies for the yaw misalignment of turbine 1 as a function of time. This is the yaw set point that the 2 different controllers are commanding. And we can see from a qualitative perspective, they're relatively similar, but of course there's quantitative discrepancies, certainly at particular times, especially during the transition period of the atmospheric boundary layer, transitioning from daytime to nighttime. The realized yaw follows similar trends, of course, but with higher noise due to the turbulence in the simulation. And if we look at the energy gain compared to baseline yaw line control, we can see some interesting characteristics. We can see that during the unstable and transition periods of the simulation, open loop control is actually decreasing power compared to baseline yaw line control. So there's actually an energy loss by performing open loop wake steering. but there's a significant gain using open loop control during the stable, more steady part of the simulation. And overall, the closed loop methodology has a much higher gain during the unstable and transition period, performs similarly during the stable period, and if you integrate over the full simulation, has a slightly higher energy production. Okay, so that was the story with respect to the closed loop wind farm control. I also want to talk about the role of atmospheric boundary layer shear on power-yaw relationship, the relationship between the power production of a turbine and its yaw misalignment angle. And so the first part of the talk was really focused on what's the degree of wake interactions between individual turbines, how does the properties of the atmospheric boundary layer influence the magnitude of the wake recovery and therefore the wake interactions between the individual turbines. But the potential for wake steering also critically depends on the relationship between the power production and the yaw misalignment of the individual turbines which are choosing to yaw misalign. And so the question is, how has this been predicted in the past? How have we predicted the power production of yaw misaligned turbines? Well, historically, we've used actuator disk theory for this. So if you start with actuator disk theory, we make assumptions of one-dimensional uniform flow and uniform thrust over the rotor area, and we make assumptions that the flow is steady and inviscid. And so if I put that into a graph instead of just words, we can see that the wind speed is coming from left to right, characterized by this vector U. This is the wind turbine rotor, again, a top view, where n hat is the unit normal vector perpendicular to the rotor area. So the power production of this turbine is this well-known expression, which has the dot product of the incident wind speed with this unit normal vector raised to the third power. So if I introduce a yaw misalignment, that introduces this yaw angle gamma between the incident wind speed and this unit normal vector, that dot product then gives us a cosine, which is then raised to that third power. So that's how we get this cosine cubed estimate of the power loss for a yaw misaligned turbine. However, in practice, this power loss of cosine cubed has really not often been observed. So instead, we introduce this empirical quantity. So this is called the power ratio, which is the power production of a yaw misaligned turbine divided by the power production of a yaw aligned turbine. You can also write that in terms of the coefficients of power. And this in practice has often been modeled in the past as the power ratio is approximately cosine of the yaw misalignment angle raised to this empirical P sub P factor. And if you actually look at the literature, there's a huge spread in the reported values of this P sub P factor. So in large-eddy simulations of the NREL 5 megawatt turbine, it's around 1.9. Wind tunnels have reported between 1.8 and 3. And field experiments have reported anywhere between 1.4 and 5. So we can already say that the cosine model is insufficiently capturing the physical trends associated with the power production of yaw misaligned turbines. And our hypothesis was that this was primarily associated with the assumptions of one-dimensional uniform flow and uniform thrust over the rotor area. So our goal was to develop a power versus yaw model from first principles, which accounts for spatial wind variations. And I showed an example of spatial wind variations during the unstable boundary layer simulation. We saw that the degree of wind shear, wind direction shear, and also wind speed shear changes as a function of time in the atmospheric boundary layer. And we'd really like to develop a model which can account for that variation in time. And so if we take a typical Ekman profile, so this is a typical wind direction variation that's associated with a stable nocturnal boundary layer according to an Ekman spiral, and we yaw align a turbine here. So I know it's a pretty busy plot. I'll walk through this step by step. So first I'm looking at a front view of a yaw aligned turbine. And so we yaw align it, which means by definition, we have zero wind direction at the hub height with respect to the turbine orientation. The typical wind direction profile, the Ekman spiral, will then give us a lateral velocity shown in red, which is in the positive y direction. Again, this is a front view, so it's in the positive y direction below hub height, and in the negative y direction above hub height. So this is the characteristic wind direction turning that we have in the atmospheric boundary layer. Now what happens if I introduce a yaw misalignment? So typically we introduce yaw misalignment and we define it with respect to the hub height wind direction. So here I've defined gamma, the yaw misalignment, with respect to the hub height wind direction. So we've imposed this gamma here. But actually the wind direction is changing over the rotor area. So that means we're more locally aligned below hub height, given the Ekman spiral, and we're more locally misaligned above hub height because the wind direction is also changing over the rotor area. So we really need to introduce a local yaw misalignment angle, which depends on the particular r theta radial and azimuthal position in the rotor plane, because the wind direction depends on the r theta position in the rotor plane and the turbine orientation beta, which is just the heading of the turbine, which orientation is it actually facing. So then we extended blade element theory to incorporate this variable yaw misalignment angle as a function of this r theta position. And that was done in this JRC paper in 2020. Then we can estimate the incremental torque as the radial position multiplied by the incremental tangential force, and the incremental power, which is the blade angular velocity multiplied by that incremental torque. And then this power ratio, which is really this power loss associated with a yaw misalignment decision, can be computed directly as this. It's just the angular velocity of the yaw misaligned turbine multiplied by the area integral of this incremental torque contribution. That's for in the numerator for the yaw misaligned turbine, and in the denominator we have the yaw aligned turbine. And this directly gives us how much power we're actually losing by imposing a yaw misalignment for a given incident wind direction or incident wind conditions. So we were interested in seeing how well this model performs using power production measurements from a utility scale wind farm. So we actually instrumented a utility scale field experiment, which is shown in this top view here, where we have this turbine A1, and we intentionally yaw misaligned this red turbine A1 as a function of time. So we intentionally misaligned it from minus 25 degrees to plus 25 degrees in this sequence. And here's what that looks like in practice. The red line is what we were trying to follow, and the dots are the measured yaw misalignment in 1 minute averages. And we imposed this field experiment for a period of multiple months, 2 or 3 months. And so we measured the power production of turbine A1 as a function of this yaw misalignment. And we also had this reference turbine A2 and also the profiling LiDAR to measure the wind profiles that were incident to these turbines. So just to give a sense of these wind variations as a function of time, which I've alluded to a few times, is that during the daytime, we have nominally power law type behavior in a median sense at least, which is this black line. And then these different colors are instantaneous they're 1 minute average realizations of the wind profile. So they're not instantaneous, but 1 minute averages. And we can see that there's some spread in those, but generally power law type behavior in the daytime wind conditions. The nocturnal conditions, the stable atmospheric boundary layer, is quite a different story. We have the emergence of a subgeostrophic jet, which is actually below the wind turbine hub height at this particular site and during this particular field experiment, which is very interesting. And some of these 1 minute average realizations have quite a substantial negative shear over the rotor area. So now moving to what does this power ratio look like from these field data. So the dots are all of the data. Then the purple dots are the median at each yaw misalignment angle, where the yaw misalignment angle is on the x-axis and the power ratio is on the y-axis. And I've plotted 2 cosine models. So for example, cosine cubed from actuator disk theory and cosine squared, which could be, for example, some empirical estimate made using this cosine model. And we can see that comparing these cosine models to the purple curve, that neither one does particularly well. And one thing that we can actually note from the purple curve is that it's actually asymmetric. So if you look over at positive yaw misalignment, it's performing with higher power production than the cosine squared should suggest. And at negative yaw misalignment, it's actually underperforming cosine squared. So it's asymmetric. And we can see that the green model, that's our model predictions from this new power-yaw model, and it's generally capturing the trends. But let's zoom in on this asymmetry for a second. So this asymmetry is very interesting. It has higher power production for positive yaw misalignment than negative yaw misalignment. So what we did is we just took the difference. We took the power production at positive yaw, subtract away the power production for the same absolute value of the yaw misalignment at negative yaw, and then we report that as a % difference. And here we can see the data in purple and the model in green. So quite a substantial asymmetry in the power production, where here in this particular case, the positive yaw is better performing than the negative yaw in terms of the power production of that yaw misaligned turbine. And it's worth noting that any cosine model predicts this black line. So it predicts 0 asymmetry by definition. Cosine model is symmetric. So why is this happening? How can we actually explain these variations in the power production of the yaw misaligned turbine and this asymmetry? Well, it turns out that it's fundamentally related to the incident wind conditions. So if we, instead of looking at all of the wind conditions aggregated together, if we zoom in on the daytime wind conditions, which have limited positive wind speed shear, power law type behavior, and very limited wind direction shear due to the convective mixing, then we actually have the opposite trend. So negative yaw misalignment actually outperforms positive yaw misalignment. It's a complete reversal of the trend I showed on the previous slide, which aggregates all the wind conditions together. Then if we look at nocturnal wind conditions, we have that negative wind speed shear, incident flow, and also strong wind direction shear. And then we again reverse back towards what we saw on the previous slide, where the positive yaw misalignment outperforms negative yaw misalignment. So, and we can see that the green is the model, and it's capturing these trends, and the model is fundamentally capturing these incident differences in the incident wind conditions. And so the key takeaway is that whether positive or negative yaw misalignment produces more power inherently depends on the wind conditions, which are inherently changing in time in an instantaneous fashion, and certainly on an hourly basis during the diurnal cycle. And so just quickly, I'll wrap up with conclusions. I know I went slightly long. So yeah, it made good sense to us to incorporate these two themes together. So that's what we've done in this recent paper, which can be accessed at the QR code in the top right corner, which is currently in review. So we've combined this new power-yaw model that I showed in the second section with the wake model that we proposed in the first section into a wind farm flow control model, which incorporates both of those themes. And so that can be seen at that paper there. I'll just leave up ongoing work and next steps in the relevant papers, which can all be accessed in that QR code in the top right corner. I'd like to thank funding from National Science Foundation, Computer Time from Exceed to perform the large-eddy simulations, and also our partners Siemens Gamesa and Renew Power for performing field experiments. And with that, I will take any questions.
Yeah, thank you, Mike. This was a really great piece of work. Thank you for that very nice talk. Yeah, I really like how you covered multiple disciplines, going from kind of fundamental control theory and Kalman filters to transient LES simulations. I very appreciated that.
Thanks, Bart. Yeah.
All right, questions? I see we have a question in the chat. Sure, yeah, you can unmute yourself and ask the question.
Hello, thank you very much, Bart, and also Michael for your presentation. I'll start my video and then you can see me. Here you are.
How's it going?
Okay, very nice presentation. It was a dense one. I tried to follow everything. I'm not sure if I followed everything, but in the beginning, you have like you talk about an uncertain model that you have developed or identified, a wake model. And I was wondering, so then you compare, you say that model, when you use that in an optimization, that you can get some improvement of your wind farm performance. Is that correct, right?
That's right. Yeah. So that's what we showed in this JRSC paper in 2021. And the key idea here is that, yeah, this is all still for wake steering applications. So the idea is that instead of just making a wind farm control decision based on the mean values of the parameters, we try to incorporate our sense of uncertainty about those parameters in our decision making for the yaw set point. And this follows a lot of really nice work from NREL and others, Julian Quick and others, which showed that incorporating uncertainty in the incident wind conditions helps to make improved wind farm decisions.
I see, nice. But I was wondering actually, because this is the question, so did you also compare now with, like you have like this optimization with an uncertain model, did you also compare then if you do not take this uncertainty into account in your optimization with a deterministic way, let's say? Because I'm wondering maybe, you know, maybe with the uncertainty, and if you do then the deterministic way, that you get somehow a mean or something, and that you end up maybe with similar results, or at least I would expect if you do the stochastic way or the uncertain way, that your control will be a little bit more conservative. And I was wondering if you have...
That's exactly right. Yeah. So yeah, that was the focus of the comparisons in this paper, essentially, is that we compared it, of course, to baseline control with no yaw misalignment, but also with this deterministic approach where you only have theta star, the estimate of the model parameters, which try to minimize that data space discrepancy. And exactly the approach was more conservative when incorporating the uncertainty, and we found that makes a primary difference in the unstable part of the boundary layer. So during the daytime, essentially, when you have higher variations in your wind conditions, it makes you less vulnerable to essentially noise in the measurements.
Yeah, I see that. Yeah. And I was wondering if you use also in this optimization, because it's not an easy optimization, I guess. I don't know if you have constraints also involved there.
Yeah, in this particular study, we didn't. But one could do that. Yeah.
I think then it becomes even more complicated, I think. But yeah.
Right. Anyways. Right. Yeah.
Hey, nice. Thanks for your answers.
Great.
Yeah, thank you, Stuart. All right. Does anyone else have a question for Mike? If not, then I'll ask a question in the meantime. I really like how we're moving to kind of closed loop control more recently, and then now we're using kind of dynamic filters, dynamic models. I was wondering, have you looked at the stability of your control solution? And do you think, is there a chance that your Kalman filter or your model somehow starts to diverge?
Yeah, and this is a very important question, and I think it relates to a topic which I didn't touch much on in this short talk, which is the time averaging associated with the comparison between the data and the wake model, which is really a fundamental question still outstanding, I think. So of course, the wake model that we're using here, it's a steady state wake model, so it necessarily assumes essentially an infinite time average, which of course is not true in the field data. And so as you continuously decrease that time averaging length in this comparison between the wind farm data and to make the parameter estimates, yeah, certainly it becomes more vulnerable to variations in the incident wind conditions. Yeah, we were quite concerned at first about the stability of the approach, especially because as you yaw misalign, then you continue to estimate your parameters based on the data which incorporates yaw misalignment. We thought that would be a major benefit in some sense, because the offline calibration doesn't include the parametric dependence of the yaw misalignment itself on what should the wake model parameters be, which it should, of course, depend on that to some extent. Yeah, we didn't find it in practice in an empirical way, but we haven't proved it in a pure theoretic way.
Yeah, thanks. Yeah, so at least it's reassuring that for now, with these timescales, we're on the safe side, or it seems like it.
Right. Yeah, and I think in practice, if one were taking this to a field experiment, one should have safety checks, certainly. Yeah, as with all control. Yeah.
All right, I know we're far over time, but I see Misha has another question. Yeah, Misha, go ahead.
Hi, Mike. Thanks for the talk. It was really interesting.
Nice to see you.
Yeah, good to see you. I mean, this is maybe pretty much a direct follow-on from what Bart was asking. He jumped in ahead of me. I mean, as I understand it, the gradient based optimization that you're using is still on the steady state model, and so you're finding maybe uncertain but still sort of steady state optimal yaw angles. And I guess I'm wondering is whether these transitions, these day to night transitions, say, are happening fast enough that, especially for larger farms, there might be a need for dynamic models. I guess I just wondered whether you think that a dynamic optimization model is necessary, or whether the steady state model captures enough that.
Yeah, I think it's a core question which I think requires future work to address it. I don't have a good answer yet, but it's certainly an active area of research which is very important to do. So I think the first, it's related to several different questions maybe. So at a high level, your question about are the transitions in the atmosphere happening with fast enough timescales such that we need to adapt in this way, that depends on the site-specific characteristics. So it's worth noting that the diurnal cycle simulations we've done, they're a step towards the real atmospheric boundary layer, but they're still quite idealized. So we have wind condition variations that are only coming from variations in the heat flux. We don't have, for example, meso-microscale coupling. We don't have fronts passing through the wind farm, which can cause much more rapid time variations in the wind conditions. And so I think in those kinds of settings, also incorporating heterogeneity across the farm, these things are very important to address. In terms of capturing dynamic effects, that also depends on what your objective is.